Good evening, everyone, and welcome to the first session of 2025 of the Reading Group. And today we're going to be discussing the research paper, The Art of Latency Hiding in Modern Database Engines. Now, in this paper, before we get started, the one thing I want to share with you, which you all will find quite interesting as we discuss this paper, is that many points in this paper will come across to you as quite obvious in the sense that when you hear the points, you'll wonder that, hey, that seems very easy. Why hasn't anyone thought of that before? And the reason which you'll notice as we discuss is that it requires a lot of deep observations in how database engines work today, what type of problems they are working on solving, and what problems they are ignoring. So fundamentally, the authors have noted that there are some problems in database engines that are being ignored today, and they are working on addressing those problems and addressing them effectively so that for modern workloads which don't fit in memory, because when you're dealing with terabytes and petabytes of data, it's not going to fit in your memory. It's going to spill over to storage. How do you make database engines that can deal with that effectively? So with that, let's jump into the first point, which is the types of systems that the authors are actually targeting in their research paper. So an interesting point that comes across is, yes, they do target multi-core CPUs, which is common today. Even smartphones have more than one CPU core. Large amounts of main memory, yes, more and more memory is coming into systems. But the third point is the most interesting one, because whenever you think about any system and its storage, normally discussions even in university and operating system courses revolve around hard disk drives, right? We even learn how a hard disk drive works, what are the mechanics of a hard disk drive and all of that. But never do we discuss SSDs. We never discuss those at all there. But the authors have only focused on SSDs in their discussion. So it's quite neat to note that the field has moved on and we're actually looking at SSDs as a common way to store memory, to store data, and how that can be used effectively to solve problems. And also each of these components, no matter how powerful, can be a source of latency, because at the end of the day, data can't come instantly to your CPU. It will take some amount of milliseconds or microseconds, and that latency is unavoidable. So the whole idea of this paper is, how do you make this latency invisible to an end user? How do you make it such that the end user feels that the system is always doing some useful work? It's always processing some transaction, something is happening, and the system doesn't look stuck. So that is the core idea of this paper, which is addressed to many different solutions put together. So the first solution that the authors note, which even systems today do, is how do you hide data stalls? That is, how do you hide latency that comes because you're getting data from your main memory, which is your RAM, to your CPU cache? Now, this is a very, very common source of latency because not all of your data can fit in your CPU cache, because CPU caches are normally in megabytes and your main memory is in gigabytes. So the whole idea here is, when you're getting data from your main memory to your CPU cache, how do you make the CPU do some other useful work? And how do you ensure that when the CPU comes back to this original task, the data is already in your cache available for you? So as part of this, the authors note that one very common reason for data stalls is this problem of pointer chasing. And this is a problem we all already know. Many of us may know it by another term, that is, always use arrays over linked lists, or always use vectors over linked lists. The reason people say that, and it's a very popular thing even online everyone says, is because of this pointer chasing problem, which looks something like this. So this is a visual of how your main memory would look. And here what you notice is that we have a linked list in memory, right? Its nodes are spread across memory, and this is how normally linked lists also look on your system. They are not linearly placed. They are just spread across your program's heap space. And what you'll notice is that when you jump from one node to the other, say you're jumping from the head node of your linked list to, say, the second node of your linked list, what you're seeing is that you're jumping from one corner of your memory to another corner. And this jumping is something that CPUs or hardware can never predict. They can never even think that you're going to make such a big jump from one instruction to the next. And because of that, your data won't be in the cache, and you'll have a cache miss, and you'll have to pay that latency of getting the data from your memory to your CPU cache. And that is where the expense comes from. Now, I think I should cover this too here. I think this is something which is a question many people would have, because whenever you think of operating systems and when we learned about caches, we would have heard about this term of spatial and temporal locality. And that is true for caches even in the author's paper that they have considered. But the point is that these two concepts don't help here because the data that you're accessing, first of all, is not the same piece of data. So temporal locality doesn't help you. And the data that you're accessing is in some other corner of memory, right? It's in some other place of memory. So even spatial locality doesn't help you because you're not accessing data within the same radius of the original piece of data you were using. So, how is this solved in systems today and how is MosaicDB solving it? It's a common approach and it's a very interesting approach that is solved by CPUs in the hardware. And that is with using prefetching instructions. So, these are CPU instructions, they are available in your hardware and they're very, very common. Your laptop probably has them, even your smartphone today probably has these instructions available. And these are asynchronous instructions. That means they happen in the background, where what you can do is you can instruct your CPU to get some piece of memory into your CPU cache. And that's a very powerful concept because you, as a programmer, can now tell your CPU to get some very specific piece of memory to your CPU cache. And that gives you a lot of control because if you go back to the previous example, if you could tell your CPU to take from node 1, if it should load the data of node 2 in advance, automatically when you go to node 2, it will be in your CPU cache and it will be a cache hit. So then you avoid data stalls at that point. So that is a very powerful instruction available to you. And I did a bit of digging around apart from the paper and I actually found the actual instructions that you get, whether it's an Intel system or it's an ARM system which would run on your smartphones, or if you have an Apple laptop, that also probably runs it too. So these are the actual instructions that can do this for you. And the way these instructions are used in conclusion is that when one transaction or when one task needs to fetch data from memory to cache, it will issue this instruction. So the CPU is going to do this in the background. And at the same time, you can start processing some other work, some other task. So that way, when you finish the other task and you come back, all the data is loaded up for you and you have a cache hit. So it's very seamless, very smooth, and the latency of data stalls gets hidden in the background. So this is the first approach which is existing in industry today. Any modern database engine does this, and even MosaicDB does this because it's a very effective approach to the problem. So I'll quickly pause here for a couple of seconds if anyone has any questions about what we have discussed till now about the prefetching approach, and then we'll move on to the deficiencies of current systems.
Hello?
Yeah, go ahead.
Yeah, I did not understand the part where you said that for linked list,
Mhm.
it will miss, like, it will cause a cache miss. Can you repeat that one?
Sure.
Why it will happen?
Sure. So the reason it would happen is, say that you're currently, or say that your program is currently accessing the head of the linked list, which is this one over here. So what would happen is that from one node of the linked list, you want to go to the next node of the linked list. So in our program, what do? We say node is equal to node dot next, or node is equal to node arrow next, depending on your programming language. But what happens underneath when you write such a line of code is that your program has to get this memory address, which is in the head node of your linked list, and then go to that address to access that next node. And the problem is that this address, this memory address, can be in some other corner of your memory, right? It can be at some other place of your memory. And there is a very, very high likelihood that that address is not in your cache already. So when your CPU tries to go to that address to access that node of the linked list, it's not in your cache. So it's a cache miss. And you have to get the data from your main memory. And that is expensive. And that is the problem of data stalls.
Okay, so you are assuming that the cache will be stored, that will be a contiguous part of the main memory.
Yes, caches always do that. That's because of the spatial locality property. Caches always store the address that you ask for and nearby addresses. So in linked list,
Okay,
that never happens. Normally, your node is at some other corner of your memory, so you'll most likely land up in a cache miss because that data won't be in your cache.
okay, understood. Okay.
Perfect. So with that, I think we are good with the initial section. And
Hey,
yeah, go ahead.
hey, I had a question. So, I wanted to understand a little bit more about prefetching of instructions.
Mm-hmm.
I didn't understand the stuff where you said the prefetch when you prefetch an instruction, right?
Correct.
So in the code should have the location or the address to the point that the user wants to go, right? Like if he wants to access a specific part of the memory, or it would be stored to a particular location, right? But
Correct.
that would be something that the user will input, like he wants to open image or something, right? Or he wants to basically fetch some record, right? To do that, that location would need to be clicked upon, and how that would be prefetched, like how does the database engine knows that this location would be prefetched, because the instruct the I hope you understood my question, or like do you want more clarity,
Um,
like
I,
what is
I
the
I think I got it.
prefetching of
Yeah.
yeah.
So basically, what the authors note in the paper also is that when you look at these accesses, as we were discussing here with, for example, linked list, when you look at a
Yeah.
database, the type of data structures that are prevalent there are things like B trees, B plus trees, and so on. And in these data structures, many times what happens is that the access patterns are known. So, for example, you use a B tree or a B plus tree generally for your database indexes. For people who don't know, indexes are basically quick ways to access parts of your database. So, it's a quick way to access some record of your table and so on. It's a speed up essentially. So, these data structures again are linked. They again have pointers to children and so on because they're fundamentally trees. And in these data structures, the access pattern is known. You know that if you're traversing a B tree, what do? You start from the root node, then you'll go to the leftmost child, then you'll go to its leftmost child, or you'll go, say, to some other child in between. And this traversal will always tell you what the child address is. So you can call the prefetch for the child address, and while you're waiting, process some other transaction or some other task. So that way, your system is never paused waiting for data to come in from memory. It's always doing some useful work, which in this case is processing some other transaction.
So essentially, you want to say like whatever you want to query,
Correct.
uh, database engine would try to basically cache the location of that particular block in which the data is stored by basically going through the access pattern uh, of the basically the instruction that comes in, and that's how it basically tries to improve the performance, right? Like
Exactly.
something like that, right?
Exactly. It's all about optimizing that access pattern on the data structure because the algorithms are always fast. Those are just the instructions. But accessing the data structure, especially these ones that use B trees, B plus trees, that can be slow
Yeah.
if all your data is not in the cache. So this helps there, as you mentioned.
Okay. Thanks.
Perfect. So um, I think with that, we are good on questions for this section. And yeah, this is quite a neat section. And even when I was reading it, what surprised me the most was the fact that these prefetching instructions exist. Normally, we are taught that caches are something which you can't have any control over. Caches automatically, because of locality, bring things into cache from memory, and they do it themselves. They are like a invisible piece in the memory hierarchy that we have learned. But the fact that CPUs allow you to access them or at least instruct bring some data into the cache on demand, that's a very very powerful concept. And so that's one very neat takeaway here. So with that, one point that the authors note after this is the places where current database engines fall short, because we know that current database engines handle data stalls. We saw how they do it and we saw why they do it. But there are many other places where you can have latency, or I would say a very good amount of latency, which today's database engines don't solve. So mainly those come under three sections, which has been noted in this diagram. This is taken from the paper itself, and it very beautifully shows the different types of latencies that aren't handled. So there are three, which is one related to OS scheduling and oversubscription. What this means in a nutshell is that if you run too many threads on your CPU is just going to be stuck switching between those threads to ensure that every thread is progressing, right? Because again, your CPU should make sure that no thread starves. We know this as the starvation property, which we have learned in operating systems. But the problem is OS scheduling is very heavy. Think about it, right? Your operating system has to look at all the threads, decide which one to run, then run that thread. And the worst part is that the OS scheduler runs in the kernel space, right? We know that there is a user space where your programs run, there's a kernel space where the operating system is. The OS runs in the kernel space. So your program has to switch to the kernel space, run the OS scheduler, pick a thread, come back to the user space and run again. So that is very, very, very latency heavy. But today's database engines don't solve this problem. They just take the latency as it is, which is not good. Second is of synchronization. So this is basically what we learn in terms of lock contention, right? Multiple threads are fighting for a lock. This is essentially that, which again is not handled in today's database engines. If there are multiple transactions fighting for a lock, they just let it fight for a lock. They don't try to control the access. And finally, storage IO. So this is essentially that if you're accessing storage, that means you're accessing your SSDs, right? SSDs are very fast, much faster than hard disk drives, but they're still slower than your main memory. So how do you hide the latency of getting data from your storage, right? That is again something which today's database engines don't handle at all. As we go forward in today's discussion, we'll be talking about how these types or these three types of latencies are handled and the novel approaches that the authors have come up with. So essentially here I'll just go through this part quickly because this is the same thing as I mentioned now, that databases can be very large, they may not fit in your memory. So if the data you want is sitting in your storage, how do you get that from storage and at the same time hide that latency so that the user doesn't see your database stuck just waiting for data to come from storage, right? It should always be doing something useful, some useful work. Another one is synchronization. So again, if you're contending over a lock or any shared piece of information, how do you ensure that the contention is as less as possible so that the system can run smoother and it gets stuck much lesser? And finally, the other concept is of oversubscription, as I mentioned earlier, which is when you have more software threads than the physical CPU cores. Practical example, say you run a 4-core system and on top of that you're running 20 threads. So each of those 4 cores has to handle 5 threads, assuming an equal distribution of threads to CPU cores, right? That is very heavy because your OS scheduler has to again and again kick in, switch from one thread to the other so that progress is ensured, and that is very expensive. So what the authors note in the paper, which I found a very nice observation also, is that in today's database engines, what happens is that people launch multiple threads, as I mentioned, right, 20 threads on 4 cores, for example, and they let the OS scheduler do the scheduling job. So they are completely offloading the work to the OS scheduler so that they can smartly write lesser code themselves and they can, leave the scheduling job to someone else. But the problem is that the OS scheduler is quite heavy. And because it's quite heavy, it adds its own latency, its own waiting time. So overall, in terms of saving time or in terms of speeding things up, you're at a total loss. The system actually slows down, or you don't get any performance improvement at best. So this was a very interesting observation because generally, even when you think of web servers, originally the idea was, especially in languages like Java and so on, when you used to have web servers, the original idea was for every request in your web server, you would launch a separate thread to handle the request, to service the request. But naturally, what happens is when you launch too many threads, your OS gets bogged down because it has to keep scheduling them and things slow down. And this is where languages like Go and so on come in. All of us know Go. And in Go, we have Go routines. And Go routines are in the user space. They don't run on the operating system directly. So you can spawn millions of Go routines on a system and the system will still run smoothly. So you can launch a Go routine per web request that you get and your system runs nice and smooth. So this is again kind of the same problem in another domain that we see, that don't depend too much on the operating system because it's not going to be fast, it's not going to help you. Try doing things in the user space so that you have minimal OS intervention. And when you have minimal OS intervention, things run faster in general, is what the authors have noted as well. So these are the 3 issues on a high level that the authors are targeting. Again, the 3 keywords are CPU oversubscription, that is trying to make the CPU do too much work. Second is contention, that is, multiple threads fighting for a lock, or I would say too many threads fighting for a lock. And third is storage latency, right? Even though SSDs are fast, they're not fast enough. So how do you hide that access latency? So those are the 3 problems which we'll be discussing solutions for now. But before we proceed forward, again, I'll pause for questions if there are any. And the floor is open. Right. So I think we are good on questions. So With that, we'll proceed forward to the solutions that the authors have come to. So essentially, what does MosaicDB? So MosaicDB is the database that the authors have written as part of this paper to prove their point. So they come up with different solutions. So to test their solutions, they made their own database. So what does MosaicDB do, right? What does the database that the authors wrote in this paper do to solve these problems? So again, we have the three problems over here. So let's look at how MosaicDB hides it. So first, the memory access latency. We already spoke about that earlier. It's the prefetching and switching between tasks. When one task is prefetching data from memory, you switch to another task. So the authors in the paper give it this name, Coroutine-to-transaction paradigm. So it's just a name, a fancy name that the authors have given, but it basically means what I just said, that when one task is getting data from memory to your CPU cache, you do some other task so that the CPU is kept busy. That's all it means. Similarly, the other type of latency, which is storage latency, which is again getting data from your storage, that is hidden by very careful scheduling. So essentially, when you have multiple transactions, the authors note that some transactions will take data which is in your memory, which is nice, and some transactions may take data which is in your storage, which is slow, unfortunately. So what the authors say is that if you carefully schedule these transactions, that is, you carefully run each transaction on the CPU, you can hide these latencies effectively. So we'll even talk about the careful scheduling that they describe. And it's very neat when you see it, the way they handle the different types of transactions and the way they ensure that everybody gets a chance to run, but the latencies are hidden because that's the core of this paper, right? We want to hide the latencies from the end user. And finally, regarding the oversubscription of the CPU and again, synchronization issues, it's the same coroutine to transaction paradigm. So again, what we discussed earlier for memory access latencies, it's the same solution. And one thing about this solution that the authors note, which we talked about earlier, is not having more threads than the amount of CPU cores, right? Don't have situations where you have 20 threads but 4 CPU cores. Avoid those entirely. Have situations where you have 4 cores and you just have 4 CPU threads. So you have a proper 1:1 mapping. That is what the authors aim for, and that is what they advocate in the paper as well. So just have 4 working threads which process your transactions. Don't have any background threads or helper threads. Don't have any of that, right? Just have 4 threads which allow you to process your transactions. That's it. So that is what they talk about. And as just described here on the whiteboard as well, just the same thing as I mentioned, that you need to ensure that you keep the 1:1 mapping to process your transactions. And everything else is handled with something called coroutines, which we talk about now. So the first solution, again, you saw it in 2 places, so it's the most popular one that even the paper talks about, is this coroutine to transaction paradigm, right? So what does this mean? So firstly, to decode the name, coroutine to transaction. Coroutine is essentially a function, but it's special in the sense that you can pause the function when you want and you can resume the function again when you want. So imagine that you wrote a normal function that, say, takes 2 numbers, adds them, and then returns the result of the addition, right? Imagine that you could pause the function after it gets the 2 numbers, and then you resume the function in the future, and say that you again pause it after it does the addition operation. And then you can resume it again to return the sum to you. So this is basically what coroutines are. They are special functions which you can pause when you want, and you can resume them also when you want. So that's the specialty of them. And transaction, again, as we know, databases are run by transactions. So the coroutine to transaction in totality means you take a transaction and you model it as a coroutine. If you have 10 transactions, you have 10 coroutines, 1 coroutine per transaction. So it's just a 1:1 modeling. And the benefit of coroutines here is, as I mentioned earlier, right? If you're getting data for a particular transaction, you pause the transaction and you move to another transaction so you can keep the CPU busy. And that's exactly what the authors take advantage of here. Say you have 3 coroutines, or again, because of the 1:1 mapping, you have 3 transactions. What you do is that, say a particular transaction is running and it needs to suddenly access memory. We suspend the transaction, in the sense we pause the transaction while it's waiting for data to come in, and we run some other transaction. So in this case, we're running transaction 3. And say that transaction 3 after some time also has to access some data in memory. So it also has to wait. Then we run transaction 2. So what you'll notice is that at no point is the CPU kept waiting. The CPU is always busy processing some transaction or the other. And this is very, very important. This is one of the highlights of the paper as well, that we want the CPU to be busy all the time. We don't want an individual transaction to slow things down. So we keep switching between transactions. The moment a transaction has to wait for some data, switch to another transaction that can be run. And this is exactly what the authors talk about here as well. So again, this is all done in the user space. That's very, very important because switching to the OS and the OS doing some transactions for you is very slow. And finally, we keep the OS scheduler at bay because all these coroutines are run on one worker thread. It's pretty much this, and if you see the paper, it's repeated in multiple places over and over again. So the explanation visually put in one place is pretty much what you see on your screen. Take multiple coroutines, have them in the user space, keep transitioning between them as each coroutine has to wait for some data to come in, keep the CPU busy all the time, and yeah, use only one worker thread underneath per CPU core so that the OS scheduler is kept asleep, it's kept at bay, doesn't trouble us, it doesn't slow things down. So I'll pause here for any questions on this model, and yeah, feel free to ask away because this is one of the first core solutions that the authors give to the latency problems.
I'm audible.
Yep, go ahead.
Maybe a lame question,
Sure.
but why the author didn't choose the OS scheduler, rather depend on the user space, not in the kernel space?
Got it. So that's a very, very good question. And the interesting thing about that is many database engines today, which are commercially available also, or even again the free and open source ones, what they do is they actually use the approach that you mentioned. They spawn multiple threads and they use the OS scheduler to schedule these threads. But the problem with this approach that the authors note, which is a very grave problem, is that the OS scheduler is not a cheap program to run in the sense that, first of all, operating system schedulers are complex because operating system schedulers have a lot of constraints. They have to take care of fairness. They have to ensure that every thread proceeds, no thread is starving for CPU. And the other big hit in performance is that the operating system scheduler runs in the OS space, that is the kernel space, and it doesn't run in the user space. So what happens is you have to always context switch to the OS, run the OS scheduler, and then context switch back to your program to pick the right thread. And that takes a lot of CPU cycles. It eats a lot of time, and that can cause issues where technically your system is not speeding up. It's actually slowing down because now the OS's latency, that is the time taken by the OS scheduler, is also adding into your waiting time. So you're not optimally using your CPU cycles at that point.
Got it. Maybe this is the same thing that Golang improvises on the Java threading system. Correct me if I'm wrong.
Exactly, that is precisely where it comes from. That Java suffers from only using OS threads, and that is also one of the reasons why when you have a Java web server, things get a bit tricky because you can't launch a thread per user request because things slow down very quickly if you get millions of requests. But in terms of Go,
Yes.
in the user space, it's very, very easy. Launch lightweight user space Go routines, switch between them at your will, and yeah, no operating system involvement, very fast and cheap.
Got it. But I was a bit curious, why weren't the earlier authors directly use the user space threads rather dependent on the kernel space or OS scheduler?
So, at least from the paper's perspective, the authors don't give any reason why earlier work never looked into this. But personally, what I have noticed is that this whole concept of having threads in the user space and switching between the threads in the user space is more of a recent concept, at least a recent mainstream concept, compared to having operating system threads. I would say having operating system threads is a very initial concept that dates back to the time Java came in. Like I remember one of the main reasons why Java was popular amongst people is because Java gave you one API which would work on any platform to spawn a thread, whether you're using Windows, you're using Linux, or you're using Mac or whatever. So around that time, the 2000s time till around 2014, it was very common to think of OS threads only. It's only more recently with languages like Go becoming mainstream, even Rust becoming mainstream and so on, that this whole concept of virtual threads or threads in the user space has become very common. Just to give you one more interesting statistic, even C++, which is a very performance oriented systems language, which is also quite old and it's been evolving over time, even that introduced this concept of coroutines in C++20, which came in the year 2020. So it's quite a recent phenomenon to think of this approach. So I think that's a very strong explanation why others never thought about this, because it just wasn't a common way of thinking when it comes to running things concurrently.
Got it. Yeah, thanks. Thanks for the answer.
Thanks.
Hello, am I audible?
Yep, go ahead.
Yeah, just a small doubt. In between the coroutines,
Right.
is there a CPU cycle being consumed?
So for this, essentially there are the coroutines that the authors talk about in this paper are called stackless coroutines. And technically, don't worry too much about why it's stackless, but it's a type of coroutine which is very fast to switch between. So if you have two stackless coroutines A and B, switching between them is very, very fast. It's very, very cheap. So switching between them is not a problem at all in terms of latency or performance.
Okay, got it.
Hey, do we have any benchmarking on like how much percentage there's an improvement on adding new coroutines?
So from adding coroutines, I think this is in the paper under the evaluation or performance section. I have the paper over here. Just let me know if it's visible. I've just switched screens.
No, I think
It's not visible.
it's not as me.
Oh, it's not. No worries. Then I think what I can do is, I think this is the one. So what I can do here is, if I take a photo of this and try bringing the photo into the whiteboard, I think that might help. So yeah, just improvising here. So this is one of the stats from the paper where what the authors have done is they have actually increased the number of coroutines that are running, the number of transactions they take in a batch. One is 4. So basic sequential means 1 at a time. 4 means 4 at a time. And 8 is 8 at a time. And if you see in the throughput, you can actually see that when you have more transactions to switch between, the performance actually increases over time, even though there is high contention and you have an insert only workload. So inserts are more expensive because inserts are actually write operations. So you have to manipulate data, you have to make sure the data gets written to disk because we have to maintain the ACID properties. Even then, the performance is quite good and the throughput is very high.
Okay.
And one interesting point I just want to touch upon a bit more. Maybe I'll skip to this because the question came in and it's a really good question, which is about coroutines itself. So essentially, coroutines, as we all know now, are functions which can be paused and resumed at certain places on demand. And these run in the user space, right? That's one of the reasons they are special compared to normal operating system threads. But the thing is that there are actually two types of coroutines which exist in multiple programming languages. Your programming language generally has one or the other. I don't know of any language which has both. So that's an important point to keep in mind. So sometimes your language choice when you're building something can make a difference in your performance. So specifically when we talk about stackless coroutines, which is what the authors use in the paper, this is something which you get in more performance oriented languages like say C++ and so on. And the specialty of this type of coroutine is that this coroutine, that is this function, doesn't have its own separate function stack. It uses the same stack that the thread has. And because it reuses the same stack, it's very resource efficient, right? It's very frugal, if you want to put it that way. It doesn't have its own stack. It shares the stack of the thread when it's running. And when it's done, it removes itself and stores itself in memory. It doesn't keep its own separate stack. So that is a very frugal approach, a very resource efficient approach. And because the thread stack is shared all the time, that stack is always available in your cache. So again, you have a lot of cache hits as well. So because of that, the performance of stackless coroutines are generally better. Stackful coroutines, as the name suggests, are coroutines where each and every function has its own stack. And all of us here know an example of this type of language, Go. Golang actually has Stackful coroutines or Stackful coroutine like Goroutine threads, because every Goroutine has its own minimal stack, which is custom to it or personal to it when it runs. So Goroutines are fast, but when you look at Stackless coroutines which C++ and other languages have, which are more systems and performance oriented languages, those turn out to be even more faster. And again, the reason why you would choose one over the other is the trade off of convenience versus performance. Stackless coroutines are very performant, but they're not as convenient to use. They have certain constraints in terms of things that you can do. But Stackful coroutines, they're just like OS threads for you, but they're not as performant because every time you switch to a Go routine, you have to load its stack also, which could be large and which may not be in your CPU cache. So that is a trade off you need to keep in mind. So, yeah, I just want to jump to this to cover this real quick because this is an interesting trade off. Because normally you hear people say, don't worry about the language, just build what you want to build. But this is one of those cases where the language clearly makes a difference in the type of performance that you can get at the end of the day. So, again, I'll just pause here for 30 seconds. Any questions, feel free to ask away.
So we need to have a scheduler for scheduling the coroutines also, right?
Exactly, yes. And that scheduler runs in the user space. So it's not the OS scheduler, it's our own scheduler that we have written in the user space as part of our process. And these can be much more lightweight because these schedulers are only for your program. So they can be much more simpler. Number one, that's a big benefit. They're much simpler than operating system schedulers. And because they run in the user space like your program, there's no context switching overhead that's required. So that way also they're very lightweight to use.
And all of these map to a single worker thread.
Exactly. A single worker thread, you can think of it like your hardware or OS thread. Only a single one underneath. Yeah.
Okay.
And one other thing that I feel is worth covering here is just to look at a bit of a code inside or a sneak peek into how this type of code looks. So this is just a quick overview because this is particular to C++. Depending on your language, it will change, it will depend. But just to get an idea of what it means, right, for a coroutine to suspend itself and then restart itself, how it works is something like this. You have a scheduler, which, as the previous question mentioned, it's a user space scheduler. It runs in the user space as part of your process, and all it does is a simple round robin, right? Go over the transactions. If a transaction is not done, you resume it so that it can complete. That's all. You just do that as long as there are some transactions to process. Very simple, just a round robin approach. When you look at what is inside a coroutine, right, what is inside a transaction, it will look something like this. So again, when you think of transactions, just to take a step back, you'll think of your SQL queries that you give. But always keep in mind your SQL queries always boil down to some data structure access, some read to the disk, write to the disk. It always just boils down to that. So no matter what fancy SQL you write as part of your transaction, it just boils down to these read and write, change a data structure pointer, stuff like that. It just boils down to these very basic operations. So over here, this is what a coroutine can look like. So imagine you're accessing some data at address P. You call a prefetch for it. That is, you're getting the data from memory to your CPU cache. And then you suspend. That means you pause yourself. So because you want to give some time for the data to come in from the memory to the cache, right? And when you pause yourself, the scheduler will take over and put some other transaction to run. Simple. Then you will eventually be run again because of the round robin that we saw for the scheduler. And when you run, it'll be a cache hit on line number 4. Similarly, for the piece of information that is at address Q, call the prefetch to get the data from your memory to your CPU cache. Suspend because again you need to wait for some time. So you let the scheduler run some other transaction to keep the CPU busy. And again, when you come back, because of the round robin scheduling, you'll have a cache hit when you access that data. So that's exactly what happens in these coroutines and how they prefetch data, suspend, and continue their execution. So again, here I'll just pause real quick if there are any questions. This is just to give you an insight into how these transactions fundamentally look, like at the most basic level, what is happening. And this is what it is. This is how the memory interactions, prefetching, processing, how that happens.
Hi. Another question from my side. So you have mentioned that the scheduler is simple round robin. But let's say I have a use case where I need a few transactions to be very, very sensitive and few, maybe it can be okay to wait. Like let's say this is a use case from the user side. So, but this scheduler runs round robin, and both of them gets the same preference. So I guess this isn't the correct database for my use case. Am I right?
So in this paper, the way the authors have considered the transactions, um, generally the only type of prioritization they have done, and we'll see this later in the paper, but I'll mention it now that the only type of prioritization they have done is between transactions which are accessing memory and transactions that are accessing storage. That's the only type of separation that they do. But in your case, if you're looking at some other type of method to prioritize certain transactions over others, so like some are VIP transactions, some are normal, that type of approach is not discussed specifically in the paper.
Got it. Yeah.
One thing I will leave as an open statement that I wouldn't be surprised if you can make your own user space scheduler, or anyone can come up with their own user space scheduler to prioritize certain transactions. Because again, at the end of the day, even if your user space scheduler is a bit complex, you're still better than an OS scheduler simply because you're in the user space, right? You don't have to context switch to the OS every single time, which is a major saving. And that itself is quite good. So even if your user space scheduler has to be a bit complex to support priorities, it's not a loss. You're still quite good. You're still better off than an OS scheduler with only OS threads.
Yeah, got it.
Cool. So I think with that, we are good with this section. Um, Essentially, one thing that I will do now, just to go a little into what a total transaction can look like, and this is again a image from the paper itself, so credit to the authors. What I'm showing here essentially is how an end-to-end transaction would work on a sort of a block diagram level. On the top left here, we have the 1:1 mapping. So you have one CPU core, which is spawning one worker thread or one OS thread. And that one OS thread is switching between different transactions. And those transactions are all in the user space. And we saw the benefits of that right now. So say that we have two transactions in our example, transaction 1 and transaction 2. Initially, transaction 1 is running, and say it does a read operation. It's reading some data. Say that data is A. What you need to do first is you check if that data is in your memory. So in your memory, you have certain data structures like your indexes. Like I mentioned earlier, indexes are just like a quick reference to access particular pieces of data. So you check your index and you see if that data is in your memory or if it's in your storage. If it's in your memory, that's good. You call the prefetch instruction that we have discussed earlier and you suspend yourself so that you can wait for the data to come in. When you suspend yourself, naturally the scheduler is going to move to transaction 2 and process that transaction. Eventually, assuming round robin scheduling, you will come back to transaction 1. And when you come back to transaction 1, the data you need will be in your CPU cache and you can continue your execution. That is one code path. The other code path could be that when you're reading the data A in transaction 1, when you're reading your database indexes, you might find that your data is in storage. Unfortunately, it's not in your RAM, right? It's in your storage. So you have to go to your SSD to get that data. In that case, what happens? You call a separate function that issues the IO operations for you. So it issues the storage IO operations for you to start the fetching of that data from SSD to your memory. That is your system RAM. And again, while you're waiting for that data to come in, suspend yourself, pause yourself so that you can move on to transaction 2. The scheduler can move on to transaction 2 and the CPU is kept busy. So, on a high level, these are the two types of workflows that you can have. When you have multiple transactions running, accessing different types of data from different places. Either it's in your cache, which is good, it's in your memory, not too bad, or it's from your storage. So that's going to take a while to get the data. So these are the access paths that can happen. And again, I'll just pause here for a few seconds if there are any questions about this. And yeah, as mentioned earlier, this image is again from the paper, and this is used a couple of times in the paper to describe different pathways that can happen and how MosaicDB hides the latencies in each pathway. All right. I don't see any questions in the chat as well. All good. If yes, thumbs up. If everything's good. Ah, perfect. So that's great to see. So with that, the next part that I want to cover for coroutines is something which we all know in terms of clean code. So I'm just going to leave that keyword there for you as we do this, which is we all know this as clean code, have very maintainable modular code, which is, easy to maintain, easy for people to work with and so on. That type of code is not always good for performance. And you may want to write nice to maintain, good looking database engine code, but unfortunately, that database engine will only look good in your editor, in your code editor. In performance, it may not be the best thing out there. So the authors note this as what you see on the left of the screen here as a deeply nested call stack. So what's happening here is in making your code nice and modular, nice to work with, what you'll end up doing is you write a lot of functions. One function calling the next, and so on. And each function is nice. It's very specific. It has a single responsibility. It's well named, so it's easy to debug in the future. All the good stuff. But the problem is that because of this modularity, the performance is very bad because every time you go from one coroutine to the other, you have to keep switching. And switching is cheap, as one question in the past had asked, that switching is cheap, but the cost adds up over time. Think if you're going 10 layers deep, 10 switches have to be done to go to the bottom function and then 10 switches back to come back to the original caller. So 20 switches overall. That is expensive and that cost adds up very quickly. So performance takes a hit. So much so that the whole prefetching instructions that we spoke about in the beginning of this discussion, the benefit of that actually gets negated because it takes so long to switch between these coroutines and come back. So that's a big problem. And especially people who know compilers will be jumping at this when they say that, okay, this is a known problem in compilers, right? If you have a lot of functions, one calling the other, compilers do something called function inlining, right? They inline function calls. And for people who don't know, function inlining is simply if function A is calling function B, what you can do is you copy paste the body of function B and you put it into function A, where function B is called, right? You just paste it there, the body, and now you just have function A with the body of function B inlined. That is literally what function inlining is, and compilers can do this for you today. The problem is for coroutines, this doesn't always work well. So what the authors note is that this has to be done manually. You have to manually inline code. And that means you need to manually copy paste things, copy paste the body of B into function A and do it yourself and manage it. But the problem is that when you have a single large coroutine where everything is just squashed together, your code looks horrible. It's difficult to maintain. Things are repeating all over the place. Imagine if you had a function which you called in 10 places. In all those 10 places, you're going to copy paste the body of that function. Lot of code repetition. It's not going to be something nice to work with. So your code modularity is definitely out. That's not going to happen. So what about your performance? Did you get good performance at least? Because there has to be some trade-off, right? There has to be some win at the end of the day. So the reality is your performance is all right. That's what the authors note, because in CPUs, you have two types of caches. You have a cache for the data, which is for all your variables, your data structures and all that. And you have another cache for the instructions, your program's actual instructions, the if statements, the add operations, and so on and so forth. And this cache, which is for your instructions, turns out to be underutilized or utilized very inefficiently. And here's an example of it. This is not in the paper, but after thinking about it and seeing online, this is the example I came up with, which best explains the problem. Say that before function inlining, your code looked like what's on the left. You have a condition. If the condition is true, you call a certain function. Otherwise, you call another function. Simple, right? Now you do function inlining. Once you do function inlining, the entire body of these two functions is pasted here. So we have 150 lines of function A and 50 lines of function B. And now comes the hard hitting part. What if function A's code was never called? In the sense the path was not taken. All the instructions that you loaded in, all those 150 lines of code or even more, which has been loaded in for function A into your instruction cache, is all wasted. It's all useless. It doesn't run. The CPU doesn't execute it. It has just occupied space in your cache. And again, when it's wasting space, that means there could have been other instructions which could have been in the cache instead. The opportunity cost, right, of some other instruction being in the cache instead, which could have been much better for your performance. So that is a very big hit. So function inlining is not a silver bullet. It has these edge cases where performance takes a very big hit and you lose out on caching benefits. So that's why both these extremes are not good for us. We don't want to have modularity and nice to read code because that looks good on a code editor, but performance is another story. We don't want to have a single large coroutine because it's not fun to work with, not for anyone. But at the same time, performance is not that great, right? The cache utilization is very low. So we need to come up with a compromise. And before I move to that compromise again, I'll just pause here for a few for 30 seconds. If there are any questions on the issues that I discussed now, feel free to ask away.
Just a small doubt. In the coroutine,
Sure.
you told about like how to arrange the code, right?
Right.
So what exactly are we arranging, like transactions?
Correct. So each coroutine corresponds to one transaction. So the idea is that when you switch between coroutines, you're switching between different transactions. Let me know if that answers your question or if you meant something more particular about the coroutine code.
No, that answers my question.
Ah, perfect. All right. So I think on this section, we are good in terms of what are the problems with how you lay out your coroutines. So what is the compromise? So the compromise that the authors have noted in the paper, which again comes across as quite novel, is that when you look at storage accesses, right, when you look at actual code that has to access your storage, in our case the SSDs to get the data, that code path is much more complex than the code path which has to access your main memory. And we even saw this earlier. Like if you look at the, I think that image was over here. Yeah, this one. You can actually notice that to get data from your memory, you're just calling the prefetch call, which is given by your compiler. And underneath, this is just calling that CPU instruction, either prefetch or prfum if you're on ARM. So it's just that much. It's such a simple code path when you're accessing memory. But when you need to access your storage, your SSD, that code path is much more complex because you have to deal with storage access APIs like IO Uring. Some of us would have heard of this term, IO Uring. It's a library for accessing storage efficiently. You have to access that library. That library will have its own internal function calls. So it becomes very expensive. So what the authors note is that accessing storage is quite expensive in terms of the code path compared to accessing memory. So maybe there we can do some trade-offs in terms of keeping one code path nice and modular and easy to maintain, but we keep the other code path inlined or squished into one function as much as possible. The second observation is that accessing storage, and we know this one, accessing storage takes much longer than accessing memory. That's just the reality that we have to deal with. So, because of that, what if we switch to these storage accessing coroutines lesser? Because again, we know they're going to take longer, right? So why access them often? Just access them, rarely, once in a while. But the coroutines that access memory, that is your RAM, access them often. So that is another trade-off that the authors look at. And the benefit is that the storage coroutines, which you can think of as nice and modular, because again, they're complicated code paths, so keeping them modular is good. Even if calling them each time is heavy, takes a lot of time to call, get the coroutines running, and so on, you do them less frequently, right? So fewer but longer calls is the same as frequent but shorter calls. So it amortizes over time. And this amortization is something which can benefit you a lot. So this is the two observations that the authors made, and they come up with this design of selective coroutine nesting, which means certain coroutines you nest, certain coroutines you don't. You keep it flat. And this is just a visualization of it. Very intuitive for coroutines which are accessing storage. Keep them nested, right? Because anyways, we are not going to access them often. That's why we amortize the cost, and we keep them nice to maintain and readable. But coroutines which access the memory, those you can keep as a two level. You have your transaction accessing the memory coroutine or the memory helper functions. That's it. So this way, you maintain your performance, which is what we want from a database engine, and we keep the code readable, maintainable, all the clean code stuff, right? All the nice stuff that we like as developers from our code. So this is mainly the solution that the authors come up with, and this is how they've even structured their code in the database so that they can keep these two properties maintained. And finally, in the diagram that we saw earlier, you can actually see this nesting at play. If you're accessing your storage, you can see you have these three coroutines. You have your transaction coroutine, which calls the read coroutine, which checks where your data is, and that calls the access storage coroutine, which actually does the storage access for you. And also you can see the OS and the IO functions which have to be called underneath. So a very deep nesting is happening, right? 3 or 4 functions, one after the other. However, in the case of the memory accesses, you have just your transaction and you have the read operation. That's it, just two levels, from the transaction to the read and then back. So that's what selective coroutine nesting is, and that's how you balance the two extremes of performance and code maintainability, or as I'd like to call it, clean code. That concludes the whole coroutine design, how you create them, how you write them, specifically like what we saw now. And we'll now move to batch scheduling. That is, how do you take a batch of tasks or a batch of transactions and switch between them efficiently. So batch scheduling fundamentally is about how you take a batch of transactions, finish them, in the sense, fundamentally what happens to a transaction. Either you commit the transaction to your database or you abort the transaction, right? We have learned this when we look at database courses and SQL language syntax, right? That you can commit a transaction or you abort it at the end. So essentially, when you look at a batch scheduling, you're looking at taking a batch of transactions, again, a batch of coroutines, running them to completion, that is finishing the batch. So every transaction has either committed or aborted. And once you're done with your batch, you move on to the next batch. That's it, right? Very, very simple, very easy to understand approach. Take a batch, process it, finish it, and then move on to the next batch. But this very simple approach doesn't work well when you're dealing with a mix of workloads, right? When you're dealing with data in your memory and you're dealing with data which is in your storage, in your SSD. The reason why it doesn't work well is because of two reasons which we'll dive into deeper now and we'll discuss it. It's quite interesting. One is that the scheduler needs to check, right, if a certain IO access is finished or not. That means if a certain memory access, that is like your prefetch instruction, or if a storage access, that is your asynchronous IO instructions to your SSD, if those have completed or not. How does the scheduler check this? Fundamentally, your scheduler can only check this by resuming the transaction and seeing if the transaction has completed that operation or not. And at first, this might feel very obvious, right? That how do you know if something is done? You have to run it, see if it's done, and if it's not, you have to move on to some other transaction. But the authors note that this can be very expensive to do, simply because imagine an IO access example, right? If you have an IO access, we already know the coroutines are very nested. You're going to switch to that transaction. You have a deep nesting of coroutines, so you have to load up each one, and then you check if the access is complete, and you realize that, oh, the access is not complete. So then you have to unload all those coroutines and then switch to another transaction. That is very expensive. That is very expensive, and it takes a lot of time. And imagine if you have a lot of transactions in your batch, and for almost every storage oriented transaction, you're doing this expensive and even wasteful operation, because you can't resume the transaction because unfortunately it's not got the data it needs. So you just have to suspend it again and switch to another transaction which hopefully has got its data. So this is a problem, and the authors note it as again the same points that I mentioned. The call stack is nested, so it's very expensive to switch to that coroutine again and again. And IO requests are slow, right? So you'll be coming to the same transaction multiple times, and you'll every time realize that, oh, it's not done. Okay, move on. It's not done again. Move on. And this becomes quite heavy for your system, and it eats a lot of time. The solution that the authors note is that instead of resuming the transaction every time to see if it's done or not in terms of getting the data, store the status outside the transaction, right? Store it in the worker thread so that when you're checking if a transaction has finished getting the data it needs, you don't have to resume it. Just check in that separate data structure if it's got the data it wants. Then you know the transaction is ready to be run again, and then you can run it again. The most beautiful analogy I can think for this is how in operating systems we learn about the state of a process, right? You have a process in the ready state, you have a process in the running state, and then the process can be in the waiting state, right? We know these states of a process. Similarly, we are creating a state of a transaction here essentially, and we are keeping a separate data structure to keep track of the state. So is the transaction waiting for IO? Is the transaction finished getting the IO that it needs? So it's in the ready state. Or is the transaction already running? That means the transaction is already resumed. So we are keeping a data structure separately to track these things. And we check this data structure first before resuming a transaction. So that is the beauty of this design, and that's exactly what the authors have done here as well in this example. You have a transaction which is memory bound, which is running. Then you move to a storage bound transaction, you check if it's done or not. In this case, it's not, so you skip it. You don't even resume the transaction, you just skip it. Then you move to another memory bound transaction, it's done, you resume it. Then you cycle back. The first transaction is still waiting for data to come from the SSD. You skip it again. You run the third transaction because it's got the data it wants. You finish running it. Finally, the first transaction has got the data it wants. Now the batch is complete, so you can take a new batch of transactions. So this is the approach that the authors come up with. So now, because of this, you don't have to resume your transaction to check if it is done. You can just check this separate array or this separate data structure, which is outside of any coroutine, which is with the worker thread itself, and it knows when to resume or when to not resume a transaction because it's keeping track of the state on its own. Just like how in OS scheduling, we keep track of a process state, right? Whether it's ready, running, waiting, or finished. Same concept applies here. So this is just the scheduler logic, just as I mentioned earlier. The only thing that I will add here is that the reason why we always have to resume a transaction if it's waiting for memory is that transactions which are waiting on memory, there's no way to check if the data has come into the cache or not. There's no way to verify because CPUs today fundamentally cannot tell you if the data is in the cache or not. So there is no assembly instruction, there is no machine code available with which you can ask the CPU that, hey, is this piece of information in the cache or not? So that's why you have no choice but to say, okay, if this transaction is waiting on memory, hopefully that data has already come into the cache, so we just have to resume it. So that was something interesting that I also found. So that's what this approach comes down to, and how we prevent the latency of reloading a transaction to see if it's got the data that it wants. So this is the first problem and its solution. Let me know if there are any questions about this, and if not, we can proceed further. Oh, okay, there's one question in chat. The worker thread, it has all the details of transactions. Okay, so yes, the worker thread has to keep track of the status for every transaction. But one thing to note here is that one worker thread will not take thousands of transactions. It may take maximum 20 to 30 transactions at a time. 30 also is in the rare case, it's normally around 20. So keeping track of 20 transactions, in the sense, have they got the data they wanted from memory or have they got the data they wanted from storage, is not a heavy operation. The data structure also is quite small. You can think of it as an array of 20 elements, and the worker just has to consult that array every single time to see if the coroutine is ready to run or if it's still waiting for some data to come in. Let me know if that answers your question. Perfect. Right. So I don't see anyone typing any other questions in chat. So I think we are good to continue. So the second type of issue is that, and this you would have noticed in the visual as well, that only once a batch of transactions is completed, do we move on to the next batch? And you would have noticed this very interesting situation here, right? That this batch of size 4 has 3 slots empty. There's only one transaction which is still proceeding, but still we leave the 3 slots empty, right? That is very wasteful because think about the CPU could have had 3 other transactions to execute or to switch between, but we just leave it empty because we are going with a very naive, very innocent approach that we'll finish all the transactions that we have and then we'll move on to the next transaction. But what the authors suggest is that let's not do this, right? Let's keep taking transactions as slots get free. So as a slot gets free, keep filling in the transaction to take its place. That's a good idea because that way, if a batch size is say 20, it will always be at 20. There will always be 20 transactions for the CPU to work on. Sounds good, right? Sounds like a perfect solution. The CPU is kept busy, the batch is always kept full, there's never a free slot. However, there's a bit of fine tuning that has to be done here. Again, the approach that you're seeing on the screen here as I'm scrolling is the approach that I just said, that always keep admitting transactions as a slot gets free. It's just that. However, the problem is that you can have some edge cases here which are very undesirable and can get quite problematic. What if your entire batch gets full of storage bound transactions? Then you're in a fix because each of these transactions are going to be slow. They're going to take a lot of time to finish. And imagine that there are some memory bound transactions which are waiting to enter the batch. Now those transactions, even though the data that they want is in the memory, it's quickly available, they are still waiting for much longer. Why? Because the batch is full and the batch is full of storage oriented transactions. So that's going to take a long time. So that's undesirable. That's not a good place to be in. So the authors note that in such cases, you need to have admission control. You need to be able to control what types of transactions you take in your batch. So the approach is simple. You keep certain slots, you reserve certain slots for memory bound transactions, and the others you keep it open for any type of transaction to come in. That works quite well. It solves the problem to a very good extent. The authors actually note that for some database engines, this actually is a good enough solution. And even MosaicDB can do this. However, when you're dealing with SSDs, especially the modern SSDs, the NVMe SSDs, which you get very commonly today, I think almost every flagship or even mid-range laptop comes with these. These SSDs are very fast. And just to give you an idea of how fast they are, these are some statistics which I got. Your typical hard disk drive from the past used to have just around 30 to 150 Mbps of bandwidth. But SSDs have 500, that's the minimum they come with, to 3500 or even more Mbps of bandwidth. So that is a lot of bandwidth, and to use that bandwidth, you need to have a lot of transactions because otherwise you'll be wasting that extra bandwidth, right? What's the point of having so much bandwidth, so much speed if you can't use all of it? So what the authors note is that many times you'll have to launch a lot of transactions to actually utilize your SSD completely. And because of that, your array, which again, just the question earlier asked about, so your array can get quite long. And the problem is that when your array gets very long, just like how the previous question mentioned in chat, that if it has hundreds or thousands of transactions, that is going to slow down the worker thread because it has to check each of those 1,000 transactions every single time. People again who are interested in competitive programming might say, okay, this is an O of n problem, right? Big O of n. Every time you need to go through all the n transactions to check if anyone is done or not. And here n is 1,000 or could be even more because you need a good amount of transactions to satisfy your SSD's bandwidth, to use all that bandwidth. Now, that can be a problem because when n is very large, your transactions have to wait a long amount of time to get another chance to run, right? Imagine you have transaction 0, which is getting some data from memory. And now imagine the size of this array is size 100 because again, you need to have a lot of transactions to use your SSD effectively, right? Now, to run transaction 0 again in the future, you have to go through all the remaining 99 transactions in between, which may be storage bound or IO bound, and then come back to your first transaction 0, to run it again. That can be a long wait. A very, very long wait is what the authors note. So because of this, the benefits of prefetching data from memory, right? The prefetch instructions that we saw earlier, those can get negated. Those would be eliminated, which is not good. We want a situation where a transaction is suspending for data to come from memory, and once the data is in the cache, it instantly restarts again. That's what we want, right? But in this case, when you have so many transactions that you have to cycle through, what may happen is your transaction gets the data from memory to the cache, it's still waiting to be run again by the scheduler, and that wait itself is very long, maybe even longer than the actual data stall. So that is a big problem. And that is why we have to improvise. We can't just run with a single queue where we take mixed workloads, but we have to actually use two separate queues. One for your memory bound transactions, which have to be run quickly, and one for your storage bound transactions, which can take their own sweet time and get the data from storage once it comes in. So, this approach, fundamentally, the authors give a very deep dive into it in the paper, but fundamentally, like what is the essence of this approach which you need to take away is that number one, prioritize memory based transactions always. Because memory oriented transactions can get the data very quickly from memory to cache, from the memory, which is your RAM, to the CPU cache. They can do that very quickly. So always prioritize these transactions first. Second, always go to your storage based transactions or transactions which are accessing your SSD only after some timeout, that means some fixed period of time, or if there is no memory oriented transaction available. So if the CPU has nothing else to do, just go to the storage and see if any transactions are running there and see if they're complete and resume them. And the third point, which is again an important takeaway, is that transactions may switch between accessing memory to accessing storage. Because if you think of any SQL statement that you would have written, you might be accessing a lot of data records in your tables, right? In your database tables. These records might be in memory partially and might be in storage. So in such cases, your transaction might switch between the two queues, right? Sometimes accessing memory, sometimes accessing storage. And when it switches, you need to move it to the corresponding queue. Simple. As it moves from one type to another, you move it to the corresponding queue so that it can be scheduled accordingly. So as part of this, the authors even give a algorithm which again encompasses the same takeaways that I mentioned. I can even highlight the exact lines for each takeaway. The first takeaway is here that always check if the transactions which are accessing memory, which are the hot transactions, always see them first. Always see them first. If a certain timeout hits or if there is no memory based transaction available, then you go to your cold or your storage based transactions. Only then you go to those transactions. Then it is possible that transactions might switch from storage to memory or memory to storage. That is here on line 11. So a transaction is now going from storage to memory, right? It was cold earlier, now it is becoming hot. So we move it to the correct queue and that's it, we move on. Similarly here, you will see that a transaction is moving from memory to storage. It was earlier accessing memory, but now it's accessing storage. Again, same protocol. Move it to the correct queue, in this case, the storage queue, and proceed forward. Otherwise, take the hot transaction which is available and just resume it. So that's pretty much what this algorithm does. I know it looks complicated, there's a lot of nesting, a lot of ifs and fors, but the essence of the algorithm is simply this. Prioritize memory-based transactions over storage transactions. Only attend to storage transactions occasionally or when there are no memory-based transactions. And if transactions switch between memory to storage or storage to memory, move them to the correct queue so that they can be scheduled correctly based on the type of data they are accessing. So I'll pause here real quick. If there are any questions on the algorithm or on this approach, feel free to ask away. Okay, so there's one question in chat. Does the database automatically decide the batch size or it's part of a configuration? Yeah, so it is part of a configuration. That is a very good question. It is part of a configuration that the authors note. It's a configuration that the authors say depends on your workload. So they do give certain numbers, but they do say that you have to tune it to your requirements. So sometimes your batch sizes can be, or specifically the batch size for the hot queue, the one on the left, the blue color one. that can be sometimes of size 8 to 10. So 8 to 10 transactions at the same time. And obviously the queue for your storage has to be larger because again, SSDs have high bandwidth and you want to use all that bandwidth. So generally if your hot queue is say size 8 to 10, your cold queue might at least be 2 times that or more. So that's the general sizing that happens, but it does depend on your workload, how large your data set is, whether all of your data fits in memory, and so on. And it's a configuration, it's a user exposed configuration. You as a client can configure it as you want. Ah, perfect. That is perfect. Um, so we have just a little bit more to go, and I think we are okay on time. I think we have around 10 minutes more. So there's not much left to cover, to be frank. So we'll go through it now. With this final approach, right, that we saw of switching between transactions and switching between different queues and putting the transaction in the right queue, one thing that you need to keep in mind is that, and this is an important trade-off that the authors mention in the paper, is that when a transaction is switching from one type to the other, and when the system is under load, when I mean under load, I mean that the queues are full, right? These two queues, the hot queue and the cold queue, then you have to make certain tough decisions. And by tough decisions, I mean you may have to abort certain transactions. So even though the user didn't write abort in their SQL statement, you as a database engine have to abort those transactions. And I'll explain this in a bit in more detail now. So imagine that the storage array is full, right? There is no space in the storage array. Your SSD is full with transactions that it has to process. And now imagine that one memory bound transaction wants to access the storage. What happens? In this case, the authors note that the transaction has only accessed the memory, right? It has only accessed the memory which is fast. So let us abort this transaction to free up some space in the system and restart it sometime in the future. Because anyways, memory bound transactions are quick, right? So they can be restarted quickly in the future. And in the future, if there is space in the storage queue, it can be moved to the storage queue. The reason why this is important is because, and again, I want to take a web server example for this. Whenever you're writing a web server for a production application, many of you would have heard of this HTTP status code, right? Too many requests. When you pound a database or you pound a web server with too many requests, eventually you start getting these responses from the server that too many requests, so the web request has failed. Why does the web server do this? Why is it rejecting your HTTP request? The reason it's doing that is because it's already overloaded. And because it's overloaded, it has to make that tough decision of saying that, okay, I can't take more requests, so I reject the requests that are coming in. So I expect the client to retry those requests when the load is lesser, right? So that is a very important point. And in this case, the same type of trade-off is being made here by the authors as well, that the storage array is full, the SSD is swamped with transactions. So we can't move any transactions from memory to storage, so we abort them. However, if a transaction is moving from storage to memory, here the authors are a bit more careful. Here the authors say that a transaction has finished accessing storage. It has waited for so long for the SSD to give it the data that it wants. And now it just wants to access memory. In this case, we won't abort the transaction because the transaction has already done so much hard work, right? It's waited for the data to come from the SSD, which anyways takes a long amount of time. And now it just wants to access some quick memory, which is again very quick to access. So in such cases, the authors say that we will put the transaction in a waiting queue. They call it a staging arena, but it's just a waiting queue. And you can see this over here. This is the staging arena. So when you're going from storage accesses to memory accesses and the memory queue is full, don't abort the transaction. The transaction has already done so much work, right? It's already got the data from the SSD, which is slow. Keep it in the staging area, keep it in the waiting queue so that in the future when space comes, we can put it in the hot queue and execute it. So this is an important trade-off, especially when the database engine is under load. So that's mainly where it comes from. And with that, we are done with batch scheduling as well. So we have touched a lot of things till now. If I even zoom out just to show you how much we have covered, it's a lot. Just from the very top, right? Prefetching. I know you can't read anything at the moment. That's pretty much the point that there's a lot that we covered today, and you should really pat yourself on the back for understanding and coming all the way to this point. Prefetching, coroutines, how to nest the coroutines, how to access storage, how to access memory, how to schedule these coroutines in batches, and so on. And this was a really, really neat journey. We're just left with a very small section here, which pretty much fits on my screen. But before we start this, I'll just wait if there are any questions anyone has on what we covered. After that, we'll just cover this section and we are done for the day. We have understood the art of hiding latency after that.
Can you give me a small example of like what are the type of things for memory-based transactions and storage-based transactions in the real databases?
Sure. So essentially, when we talk about memory based or storage based transactions, the data that you're trying to access is the same in both. Essentially, records of a certain table in your database. The only difference is that sometimes those records in those tables of your database may be in your RAM because they might have been accessed in the past, or they might be in your storage if they have been never accessed in the past. So, say for example, you just spin up your database, you just started your database program. At that point, most of the data is going to be on your storage. And after some time of your database running, say you have been running it for a while, you have been giving it some queries, some transactions, then there's a chance that that same data is sitting in your RAM now. And based on what your future transactions access, the data that it accesses, again, those records of your table in your database, may be in your RAM, that is your main memory, or they might be on your storage. It's just based on how you have accessed data in the past. But the type of data is the same. That doesn't change.
Got it.
Perfect. There's a question in chat. I'll just take that real quick. Two queues are taken care of at the same thread or two queues parallelly? No. So it's the same worker thread that is handling both the queues. And that same worker thread will give priority to the queue, which is the hot queue, which is basically the queue for the memory based transactions. That's what it is. Both these queues are managed, and even the staging area. All of this is managed by one worker thread. And also, just to add an interesting nugget here, this data structure, whatever you're seeing on the screen here, is actually what is taken care of by your user space scheduler, which is run on the worker thread so that it can select the correct transaction to run next. Let me know if that answers the question. Yeah.
A follow-up question. So basically, have like maintaining both the queues by only one thread, doesn't it, when compared to having two threads managing the two queues? So comparatively, the second option would be much efficient.
Right. So that's a very, very tempting solution. But the trade off there is of oversubscribing the CPU, which is creating too many OS threads for too few CPU cores. And this is a very interesting point because many database engines actually do this today. They have these threads called background IO threads. So these are background threads which are only meant for IO transactions. They are only meant for transactions which are accessing your SSDs. But the problem is that these transactions have to be run on a separate thread so that context switching is needed. And also remember that if a transaction is switching from memory accesses to storage accesses, you have to have thread interaction, right? One thread has to talk to the other. That is again a source of contention and synchronization and overheads. So these reasons
Got it.
are why that the authors don't do that. I think overall in the paper, the authors have been very frugal in terms of being, or I would say in terms of using the OS cores the CPU cores very effectively, and they want to have everything in coroutines. Every transaction is a coroutine. We'll do it all in the user space, but in the OS or the hardware space, we just keep 1:1 mapping so that the pesky OS scheduler and other stuff don't come in our way. So that's a very, I would say, very persistent observation through the paper that I had.
So the entire thing has been that we are shifting away from the threads, right? Because they are in the kernel space.
Exactly, but we're not shifting away entirely. We are maintaining
Yeah.
just the right number of OS threads, just the right number of hardware threads, and everything else above that we keep in the user space. Yeah.
Got it.
And I think even personally, a lot of these benefits we already see when we use Golang with its Go routines. They may not be stackless, so there's still some performance on the table that we don't get, but in general we do feel the benefits. We do see that doing things in the user space, not worrying too much on the OS side, helps a lot. With that, we come to the very last section, which fits on my screen, so it's not much, and I think we are 5 minutes left, so we'll cover this one as well. So essentially, we have seen the coroutine-to-transaction architecture, right? We have internalized it by now. We know it by heart. Probably if someone wakes us up at 3 a.m., we can probably say it too. But the main help that this approach gives us in terms of CPU usage and in terms of contention, right? Because remember I mentioned earlier that multiple transactions might fight for the same piece of information. So you have to have locking and contention, right? Multiple threads accessing the same piece of data at the same time. So they have to be synchronized. So in these cases, having coroutine to transaction modeling that's over here is beneficial because number one, because you're maintaining only one OS thread for every CPU core, the amount of threads that are competing with each other to access some data is limited. Think about it, right? If you have a 4-core CPU, you will have only 4 worker threads, which means that if there is some shared resource, only 4 threads will be fighting for it at any point of time. At worst, right? At worst. If all the 4 threads want that same piece of information, only 4 are going to fight for it. Sometimes there might be only 2 threads fighting for it or 3 threads, but 4 is the maximum. However, in the other types of database engines, where you have say 4 cores and 20 threads, there are a lot more threads, there are a lot more transactions which are fighting to access a shared piece of information. And that contention can become very expensive, it can become very costly. And that is completely avoided in MosaicDB. And this is the point that I'm referring to on the right, this where you're minimizing the contention. So that is point number 1. And another thing to call out also is that contention can't be eliminated, because if 2 threads are fighting for the same piece of data, in other words, if 2 transactions are fighting for the same piece of data, they will compete with each other. You can't do anything about it. That's just life. But you can minimize that contention by keeping the OS threads in check. Just keep the same number as the CPU cores. That's it. That keeps the contention in check. Second is oversubscription. So this we have kind of seen earlier, but all that the authors say here is that any operation that the database does is done by these worker threads only. There is no separate background thread. There is no separate helper thread, nothing at all. Anything. So if you're doing checkpointing, because databases have to do checkpointing to save certain states. So if you have to recover, you can recover to a checkpoint. You may have situations where databases have to commit transactions to your storage. It has to write the data to your storage to maintain the asset properties. We all know the asset properties of databases. All of that is done by these worker threads. All of that is done as coroutines. There is no background thread. Again, I repeat, there is no background thread, no helper thread, nothing. This is very important because you don't want the OS scheduler to meddle with your system. You don't want the OS scheduler to come in, slow things down, and do the cleanup for you. So that is the second point of oversubscription. And this is just a visualization that I had of the same thing that I just said, that if you have a worker-like thread and you have a background thread, they have to talk to each other. This also, I think, partially addresses a question that was asked just now, that if they have to talk to each other, they need some shared data structure, which is again an overhead. And obviously the scheduling array for the transactions. But in MosaicDB, it's all simple. You have your worker thread and the worker thread only, and the scheduling array for the transactions that you want to schedule on it. And that's it. That's how MosaicDB saves on multiple latencies, minimizing them, and whatever latencies remain are hidden very well. And by hidden, remember, hidden essentially means that while a certain latency is happening, some other work is going on the CPU, so that the CPU always appears busy. It always appears that it's doing something of value to the user. The system is always progressing forward, and the user never feels that, hey, the system is stuck, it's not doing anything. So a nice way to think about this is if you're building an app for a phone, right? And your app is getting some data from a server. If your app freezes while it's getting the data from the server, users will probably hate your app because it gets stuck while data is coming in. However, if your app stays interactive when the data is coming in, you can still switch between tabs, you can still click things on the screen. It feels much better. It feels much more interactive. It feels much more responsive, much more alive. And that's what people want even with database engines. And that's exactly what the authors have aimed at doing with MosaicDB as well. So that covers the discussion for today. And if you heard that, that was my alarm for the 1 hour 30-minute session that we had for today. I know we are over now, but if there are any questions, feel free to ask away. We have covered all the techniques in the paper. If you have stayed till this point, you know how to hide latency in a database engine or any type of program now. All the techniques, all the tricks. So yeah, any questions, feel free to ask away. I'm also looking at, okay, I feel there's a question coming in chat, so I'll just wait for this. And also while we're waiting, if you want to see any part of the whiteboard again to ask some questions or just recap any concept, feel free to ask away too. Thank you so much. That really means a lot. We have been multiple sessions in, and I'm really happy it's been very helpful for everyone. And yeah, the next session, yeah, I think the poll will come out probably next week. So I guess we have covered everything that we need. I don't see any questions coming in chat. So everything's clear. Just a thumbs up if everything's good. I just wanted to make sure if we have all like answered everything and we've reached the summit. I think we've pretty much reached the summit here with covering this paper and all the techniques that it uses. So yep, just before going, there's a lot that was covered. Just to zoom out, just to give you a overview again. Lot that was covered, but a lot of intuitive, easy to convince yourself observations. And you can do this too. Just as a motivation, even you can do such type of things also, because it's all about observing the problem, understanding it well, and then coming with a certain design that can solve the problem. Like anything that the authors have done here is not something new, right? They're using existing APIs, they're using existing coroutines that are in C++ and so on. But they are using it in a place, in a way that's solving the latency problem. So use the tools that are out there. You don't have to create new tools, and you can solve a lot of existing problems. You just have to observe them. So that was my motivation, because I felt this throughout the paper. The authors have done a great job in observing the problems and addressing them with the tools that are there today, and you can do them too. So with that, thank you all for joining, and yep, that's it for the session. See you all in a future session. Thanks.